Hello, welcome back to Math 332. This is the second video on Chapter 2, Determinants. So in the first video, we talk about how we compute the determinants of a 2 by 2 matrix, 3 by 3, 4 by 4, and in general n by n matrices by looking at the cofactor expansions along a particular row or along a particular column. And in this video, we are going to look at the consequences or like special properties of having determinants defined in that particular manner. So before we do that, there's a corrections. So in the first video, I keep saying that the matrix A is invertible if you have AD minus BC not equal to 0, not equal to 0, not equal to 0. And but here I wrote AD minus BC equal to 0. So that's a typo here. So make sure you fix it. This is not equal to 0. And everything else that I said was right. So last time we were the last place that we stopped was looking at the determinants of special matrices, like the upper triangular, lower triangular, or diagonal matrices. Now we want to look at some special property of matrices, which is, let's look at the first one here, which is given by theorem 2.2.1. It says that if you have a matrix A, which is a square matrix, then if the A has a rows or a column of zeros, then the determinant will be equal to 0. Now, this is easy to see. I'm not writing down a formal proof here. I'm just trying to explain, to give you like a way to see why this is right. So I'm going to say, maybe let's take a 3 by 3 matrix. So I'm not giving a proof though. You have to know. If I give a proof, I cannot say that let's look at a 3 by 3 matrix. Because if you do that, then you only show that this is true for a 3 by 3 matrix. What about 4 by 4? So I'm not giving a proof. I'm just giving an explanation. So in order to make that explanations easy, easier to understand, let's look at a specific example. Let's say we are looking at a 3 by 3 matrix. All right. So suppose that 3 by 3 matrix, say the third row is equal to 0. You have rows of 0. Well, why is the determinant equal to 0? Well, from the first video, you know that we can compute the determinant by doing a cofactor expansions along this row. So if you do that, you have 0, and then you have C31 plus 0, and then C32, and then 0, and then C33. So obviously, as you can see, this is by definitions our determinant of A, matrix A, and obviously doesn't really matter what is the value for C31 and C32 and C33. This is 0. So that is clear that if you have either a row of 0 or a column of 0, then the determinant of that matrix will be 0. Okay, now the second theorem says that if you have a square matrix, that's matrix A, then the determinant of that matrix is equals to the determinants of that transpose of that matrix. Well, this is actually a consequence from this theorem in the first video, if you remember. The theorem, this theorem right here, which says that, if you have an n by n matrix, then regardless of which row or column of A is chosen, the number obtained by multiplying the entries in the row or the column by the corresponding cofactor and adding the resulting products is always the same. This gives us a way to compute a determinant, which is either you expand it along the column or you expand it along the row. It doesn't really matter. It always gives you the same answers. And one consequence of that is the determinant of the matrix A and the determinant of the A transpose is the same, because let's say you choose the second row of this matrix and you perform the cofactor expansion along the second row, and that will be the same as performing the cofactor expansions along the second column of this matrix. So they are going to give you the same number because of that previous theorem. So we see that the determinant of the matrix A and the determinant of the matrix A transpose, they are the same. All right. So the next one is theorems, which I call theorem star. It's actually in the book, but the book presented in a slightly different manners. So I'm not going to cite that theorem. I'm just going to write as our theorem star here. The theorem star says that if you have a matrix, square matrix, and if you interchange the two row of that matrix, then the determinant of the resulting matrix is negative of the determinant of A. So let me give you one example. What happened is, what I'm saying is that suppose you have a matrix A. I'm not proving though, I'm just giving an example. So again, let's look at 3 by 3 matrix. So let's say you have the first row here, the second row here, and the third row here. What it says is that if you obtain a matrix B by interchanging the row of the matrix A, let's say I interchange the first row and the third row of our matrix A, which means second row remains the same, then the determinant of this new matrix B obtained by interchanging the first row and the third row of matrix A is equal to negative of the determinants of this matrix A. So this guy here has determinant A. This guy here, by interchanging the row of matrix A, will get negative of determinant of A. Now, because of this theorem right here, so if we interchange 2 columns instead of 2 rows, we will also have the same result, which means that theorem 2.2.2 basically says that every time when you have some property for determinant which hold true for rows, it will hold true for a column as well, because of this determinant of A equals to determinant of A transpose. So you can see sometimes the books are being very careful. They will say that if 2 different rows or 2 different columns interchange. So I mean here sometimes it's being lazy or being not careful. I'm just written down the facts for the rows, but you know that if you hold for the rows, it will also hold for the column because of this theorem. All right, so this is called this is what happens when you interchange 2 rows or 2 columns for a matrix. So what happens is that you introduce a negative sign. Okay, now, so one of the consequences, so in mathematics we call it a corollary, is this. So one of the consequences of that theorem is this. This corollary says that if you have 2 rows, again, because of this, also true for 2 columns, if you have 2 rows of square matrix A, 2 equal rows, okay, then the determinants will be 0 immediately. For example, say you have 1, 2, 3, 4, 7, 8, 9, 10, and then you have 1, 2, 3, 4. So this matrix has 2 rows which are the same. So immediately you know that the determinant of this matrix is 0. Same with the column. So let's say you have a matrix B. So you have 1, 2, 3, 5, 6, 7, 1, 2, 3, 7, 8, 9, 10, 7, 8, 9. Then because this matrix B have 2 equal columns, so immediately you know that the determinant of this matrix B is 0. That is what the corollary says. Now, how do you know this is true without even going through the computations or like cofactor expansions? Now, this can be explained pretty easily. So the formal proof, the actual proof, is given right here. So you can read this. What I'm going to show you is an example I'm going to show you an example to make this proof easier to understand. Okay, so as you can see, I am not proving it. I'm just giving an example to explain. So I am going to take A, which is again 3 by 3 matrix. Now remember, if you're really giving a formal proof, you cannot say that, because once you said that, then you are actually proving for 3 by 3. What happened 4 by 4? What happened n by n? So you can see that in the actual proof, it never mentions what are the size of the matrix. Okay, so this is not a proof, just an illustration of the idea behind the proof. So let's say you have matrix A. So you have the first row, and then you have a second row. And let me say that the third row is actually the same, okay, as the first row. So you basically have this. Now, according to this theorem, if I interchange the 2 row here, the first row and the third row, if I interchanging it, you don't see that I'm doing it. I'm actually doing it. I'm interchanging it because they're the same, so it doesn't look like I interchange it. But I'm interchanging this and put it here, and then take the first row and put it on the third row. So that's my determinant of B. Now, according to this right here, the interchanging rows theorem, so we know that the determinant of B is negative of determinant of A because I obtain B by interchanging the first and the third row of the matrix A. Now, so because this determinant of B is actually determinant of A because the first row and the third row are the same, So it's just basically exactly the same like the a after you interchange it. So now you have determinant of b equals to determinant of a, and that determinant of b is equals to negative of determinant of a. So from here, you can see that the determinant of a has to be 0. One way to see it is to move these terms to the other side to obtain 2 times the determinant of a equal to 0. These are all numbers. These are numbers. Determinant of a matrix is a number. So now you are left with the conclusion that determinant of a has to be 0. So that's the proof. That's an illustration of the proof. So that actual formal proof is right here. So that is why now next time if you see that a matrix has 2 equal rows or 2 equal columns, then immediately you know that the determinant of that matrix is 0. All right, moving on. Okay, moving on. We are looking at this property. These are simple properties. We are going to look at the very difficult one. Not very difficult, but the thing says not so trivial in the third video. So these are also these pretty trivial types of property, which says that if you have a determinant, I'm switching my notation now. I'm no longer writing determinant like this. I'm writing determinant like this now. So this property says that if you have a row, okay, of which multiplied, you basically took your first row of a matrix A. So you have matrix A standard notations A11, A12, A13, A21, A22, A23, A31, A32, A33. So if you take a matrix A and you multiply the first row of that matrix with a K, okay, when you multiply just the first row, not the entire matrix, so you get something like that. So the determinant of this matrix is actually K times the determinant of this matrix, which is the determinant of A, right? If your A is this. So be very careful though. This K is only multiplied to one of the row. So if you multiply to one of the row, you can take that thing out and it will equals to that. Now the proof is not difficult. So what happened is that if you say, for example, if you took the cofactor expansion along the first row, so that determinant of this matrix, okay, will be equals to, so determinant for this whole matrix will be equals to K A11, okay, and then C11, and then K A12, C12, and then K A13, C13. Okay, so you can factor out a K, and then you have A11, C11, and then A12, C12, and then A13, C13. And you can see that this part here, how do you get C11? So C11, okay, because you are expanding it along this first row, so your C11 will be this, the cofactor, obtaining by computing the determinant of this submatrix, so that together with the sign, so that's a C11. So you get a C11, which is exactly the same as this C11. So you have the C12, so C12 is coming from here, so C12 is coming from here, and that C12 is the same as the C12 that you get from here. All right, so this C11 from here, C12 for all of the C13 from this matrix is the same as the one that you have from here. Right, so this part here is the same as that, So this one here is the same as that. All right, so this shows that if you have a row or a column, okay, of K multiplied with that, you can factor out the K. All right, so that's that. Now, be very careful because this is where students always makes mistake. What it says is that if you have a row, you can do that. Of a row of K multiplying to one of the row, you can do that. But it didn't say anything about the determinant of Ka equals to K times determinant of A. It did not say that. This is not true. This is not true. So this is not true. I mean, it's so easy to make that assumption because integrating, say, a K of fx, we are so used to take out the K we are so used to take out a k, and also for linear transformations, we have k of x. We can take the k out, and then we have t of x. We are so used to it, so we thought that a lot of students will think that this is also true for determinant, but it's not. Okay, let me show you one example. So what happened is this. So suppose you have a matrix A, which is 3 by 3, same notations. So what happened if you multiply K to that matrix and find the determinant, then you are actually computing this. Remember that when we multiply a constant to a matrix, we are multiplying it to every entries of the matrix. So every entries here will have to multiply K. So we have that. So that property that we just proved, okay, is only true if you have a row of k, right? So here you look at this row, so we can take the k out, and the resulting determinant will be this, right? We only take one k out at a time, so we have that k out. And then referring to this matrix, we can look at this k, which is on the second row. You can take that second k out, so you have that. And now you have the third row, okay, which also multiply with the k. So now you can take the k out, and in fact, what you get is k cubed. So you can see that the determinants of k times a, if your a is a 3 by 3 matrix, what happened is that you have k cubed multiply the determinant of a. So if you say that it's just k times determinant of a, that's not true, because we don't have that property. The one that we have, the property here, as you have seen the proof, is that we can only do it for a row. Okay, so for a row we have that. So now you have 3 rows, so you have to take the k out 3 times. That's the reason why you have k to the power of 3. And also from here, you see that in general, if you have an n by n matrix, so you have to take the k out n times, each row at a time. So you have that k to the power of n times determinant of a. It's definitely not k times determinant of a. So it's not this, but in fact, it is this. All right. Now, another property for determinant is that when we have the matrix that looks like this. So this is the matrix. So we're looking at the determinant of that matrix. Now, what happens if we try to compute this determinant by performing the cofactor expansions on the first row? So if we perform the cofactor expansion on the first row, we will have the A11 and the C11, and then A11 plus B11 multiply the C11, and these terms multiply this term multiply this. So we know that from the cofactor expansions. And these are all numbers. So real numbers arithmetics, we can use that. So we know we can distribute this. So we're distributing, we're multiplying this with this, this with this, this with this, and collect them, rearrange. Then we have this expression here. So remember that C11 is a cofactors by knocking out the first row and the first column of this matrix. So you're looking at the submatrix, which is this. So this is the C11, and then the C12 will be knocking out the first row and the second column, and you're looking at this together with the sign. So C12 is all that. So remember that. So C11, C12, and C13 are all referring to the cofactors of this matrix. So once after you arrange it, you will see that this part here is actually the cofactor expansion for this matrix. All right, so you A11, C11 of that, which is this, which is the same as C11 of that, which is this. So you will see that this part here is nothing but this. And then this part here is the same as computing the determinant for this matrix. So the B11, B12, B13 obviously is coming from here. And then the C11 is the C11 from here, right? You see that? So that is the same thing as the C11 from here. So actually, what happened when you compute this with the C11, C12, C13 coming from this original matrix, you are actually computing the determinant for this matrix. So you will see that the determinant for matrix A plus B might not be this. The things that we have is the very limited sense of addition. So we are not adding the entire two matrices. If we have a row of matrix, a row in the matrix that looks like this, then you can split it into two like that. But for general additions, you don't have that. So that's another thing that you don't have, which is determinant of A plus B in general will not equals to the determinant of A plus determinant of B. So determinant do not have these additive properties. It does not have. The things that it has, the thing that it has is a very limited sense of additions, which is like that. This is what it has. So this property is what is enjoined by the determinant. So this is the only thing that we have, okay? Not this one, all right? So if you have a single row, which appears to be an addition of two terms, and then you can split them up like that, but not for this one, because when you're looking at the determinant of A plus B, every element will be added, right? Every element in A will be added to elements in B. The corresponding elements will have to add it up, but we are not looking at that. The things that we have the addition of two elements is coming from here, not every single elements here. So one of the properties that does not enjoin by the determinants is this. So remember that, don't make this mistake. Okay, now we are going to look at the things that we have seen here and apply in a very special case. So this is the thing that we have seen and we want to apply it to this case. We want to compute the determinant for this matrix. Okay, so you will see that we have the A11, A12, A13, A21, A22, A33. So, and then instead of this, we have the K times A21, K times A22, K times A23. Now, this looks very familiar, hopefully, because this is kind of like you are taking your matrix A and then you do some kind of row operation on it. In fact, the row operations that you did is taking the first row, right? And then changing your first row to first row plus K times the second row to get B. So I'm saying that my A, usual notation, A11 all the way to A13, okay, A31 all the way to A33. So if you do your row operations on this matrix, exactly these row operations, and then you get the matrix B, which is the one that we've seen here. So A11 plus K, A21, so on and so forth, like this matrix here. Okay, the determinant of this matrix. So if you do one row operations, a single row operation on A, which is this row operation, you get B. And the determinant of B is what we are trying to compute right here. So that's the determinant, and that's the B. Now, according to the observations that we have seen right here, we can split this thing out like that, right? We can take this, and this, and break them into two parts. At the same time, preserving that everything that you got right here. So everything here is the same, everything here is the same. So I'm splitting my first row into this. Okay, that this is allowed. We have seen that this is allowed from the one that we have before. Now we also know, since they have one row of K, we can take the K out, right? So that's that. Now another thing is that this matrix is a little bit special. If you look at this matrix here, you can see that the second row of that matrix and the third row of the first row of the matrix and the second row of the matrix, they are the same. So because they have two rows which are the same, so by the property that we know from before, this is actually 0. So you have K times a 0, so it's 0. So what you left is this. And what is this? This is the determinant of A. So we have seen something which is very special here, which is that if you have a matrix A, and if you do row operation like this type of row operation, we have three types of row operations, right? This is one of the types. So if you do row operation, which is in this form, to get a matrix B, then you see that the determinant of A and the determinant of B is the same thing. So which means that the row operation, this particular row operation, would not change the determinant. If you have done these row operations, the determinant of A, and after you have changed it, you get the matrix B, the determinant of B, they are the same. So, but be careful though, I'm not saying that if you have done, if B is obtained from A by doing a row operations, then the determinant of this B is the same as determinant of A. I'm not saying that, because there are three types of row operation. You can interchange the row, which from the facts that we have seen before, if you interchange the row, you will actually get the negative sign. And you can also multiply a constant to a row, and then you get this, right? If you multiply a constant to a row, then you actually have to take the constant out. So row operation have three different type of row operation. Interchanging the row is also a row operations. Multiplying a constant to another row is also a row operation. For those two row operations, the determinant will change. But for this type of row operation, their determinants is the same. That's what I'm saying. Okay, right. And also, very quickly, using these facts, we can see that for elementary matrices, if you still remember, elementary matrix is a matrix obtained from identity matrix by performing a single row operations. So for this this elementary matrix, the determinant will be -1. Why is that? Because you do a row operations by interchanging row. Okay, so if you compute, if you compute the determinant of this matrix, you will have to minus, it will be same as the negative of determinant of this matrix. A determinant of identity matrix is obviously 1, all right? So you will have -1. So same thing here, the determinant of this, so you're obtaining this elementary matrix is obtained by performing this row operations, okay, on identity matrix. So you will get k times the determinant of that identity matrix, which is k times 1, which is why you have k. And so finally, the elementary matrix of this form, the determinant of it will be 1 because this determinant is the same as this determinant. We just seen that. So that will be 1 because determinant of the identity matrix is 1. Now, which means there are several things here. Important thing is that if you do a legit row operations, we would not take a 0, multiply it to the entire row. We don't do that for row operations, right? So this k here is actually a non-zero k. Okay, so it's non-zero k. So we can also make a summary and say that the determinants of elementary matrices are either 1 or either -1 or 1 or a non-zero number k, right? In particular, the determinant of elementary matrices are never 0. Okay, for legit row operation, k cannot be 0. So the determinants of the elementary matrices are never 0. That is a conclusions, a summary, very nice summary of all the property that we have seen so far. Now, how do we apply this? Well, we can apply it by trying to find the determinant of a matrix instead of going through the cofactor expansions. One thing we can do once we have all those property is to try to find the determinants by doing row operations. So for example, that's our matrix A. So we want to find the determinant. So we're using this notation here. So we want to find the determinant. So if I want to do row operations, I will have to knock out this one and knock out this one by doing a row operation that looks like this. So this matrix here is the same as this matrix by performing 2 row operations, which is this 2 row operation. But every time you perform row operation that looks like this, you don't change the determinants we have seen here. So every time you perform row operation that looks like this, you don't change the determinants. The determinant is the same, right? So because of that, the determinant of this matrix is still the same as the determinant of this matrix. Okay, so that's the reason why they're equal. There are actually 2 steps here, but I put them together. The first step will not change the determinant. The second step will not change the determinant. So I'm putting all of them together like this. And now I don't like this one because in order to do row operation, I would not want this to be 0. And this is not 0, so I have to interchange the row. So interchanging a row will introduce a negative. So I'm introducing negative. So I have this. So all the equality is traced out like this. This part here is equals to this, and then you have this equals to this. Now I don't have to do all the way to RREF because this is upper triangular matrix, and for upper triangular matrix, the determinant is nothing but the product of all these entries on the diagonal. So now with this negative, with the 1 and 3 and -5, we compute that as 15. So the determinant for this matrix is 15. So we can actually also do that using row operations instead of doing the cofactor expansions. So this gives you an alternative. So remember, important things to remember is that for determinant of A plus B, we do not have that. We only have that for this very special case. Now, so we're going to stop right here, and then we're going to talk about the third part of the video, which is now we're going to prove a very important theorem, which says that even though we do not have this property, determinant of A plus B is not equal to the determinant of A plus determinant of B. So in English, you can say in word like the determinant of the sum of the matrices are not equal to the sum of the determinant of the matrix, right? The determinants of the sum of the matrices is not the same as the sum of the determinant of the matrices. But for product, we do have the determinant of the product of the matrices is equals to the product of the determinant of that matrix, right? So the determinant of the product of AB is the same as the product of the determinant of A and determinant of B. So this is true. Why is this true? It's going to be on the third video. So I will see you there.